More integral practice. Let's use what we've learned to review some of the things we've done with integrals. Take a look at the example over here on the left. Do you recognize what type of function this is? And what would you do? We know that the capital F of t is equal to this integral. We want to find the derivative of that. I'll give you 2 hints, but the first doesn't count. That's right, it's the second fundamental theorem of calculus, and to make this a really quick problem, you have a constant going to a variable. Let us just plug that variable in exactly as it is, and then don't forget, because we're using the chain rule here, multiply by the derivative of that upper limit. Done, thank you very much. I love the second fundamental theorem. We're doing well. Example number 2, it says find the area bounded by something. What does this mean to find the area bounded by something? Well, goodness, bounded just means what's the area inside of all of those shapes? X equals 1 and 3 of the vertical lines. This is the curvy line up top. That's just another way of saying the x-axis. How will we find the area under that curve? Gosh, I don't know. What could we possibly do? Maybe we could take the integral. However, don't forget exactly what those limits might be. We're going from x equals 1 to x equals 3. I ask you to remember one logarithm value. One log without a calculator. That one would be the natural log or any log of 1. What happens when you plug in 1 to a logarithm? Nothing. No, I don't mean nothing happens. I mean the natural log of 1 or any log of 1 is just 0. It's a big old 0. So really your answer is 6 times the natural log of 3. If you don't know what the natural log of 3 is, that's fine. Neither do I. But that is the exact value, and that's your answer. Example 3. Find the average value of that function f on the interval from 1 to e. What does that mean? Get the average height. Don't forget this one. Just find the area and divide by the base, or the width, or whatever you want to call it. So essentially, don't forget that little part. It always sits right out in front of our integral. We are going from 1 to e. We are taking this. Let's see. Do you remember what the trick is for this particular integral? It's one of those special ones I warned you about. Let the u value equal the natural log. Then you can find du dx and solve for dx. Once you rewrite it, it might look like this. Well, it might look like this. So essentially, we rewrite it, substitute in. The integral of u is u squared over 2. I believe 2 divided by 2 will probably divide out to be just about 9. Then I plug in my upper limit first, my lower limit second, and that's still being divided by the width. By the way, this is a tricky problem just at the very end because e squared minus 1 can be factored. E minus 1 and e plus 1, thereby allowing us to simplify it. I know, the algebra at the end was unexpected. But the whole idea is, don't forget how to take the average value. Finally, for the last example, we're actually going back to where if you're given, and this is a type of differential equation, that means there's a derivative mixed in with everything else. But if we're going back to one of these where we know the slope of something, we can find the original equation. Remember, to do that, what we're going to do is integrate both sides. We have one small step to take just before that. Multiply both sides by dt. That gives us a chance to do this cleanly. Integrating both sides on the left, we get p. P might be a population. It might be the principal in an investment. There's so many different things you can use logs and exponentials for. They're quite common. Then you need to use u substitution. Once again, if you have something to the negative first power, look towards natural logs. Writing out what u and dt would be allows you to simplify. And by the way, 4,000 divided by 0.2 is not as the same as 4,000 divided by 2. No, 2,000 divided by 0.2 is 20,000. So when you do that, make sure you get it right and always back substitute so your answer is written in terms of the original variables.